Thank you so much. And I'm super excited to be here. I am delighted that this conference exists, that it was created. And could we give a round of applause to the conference organizers? They've been working super hard. And have done the moving of the mountains and the acquiring of the foods and are just general amazing people. Hello, I am Paige Bailey. I am a person. I work for Microsoft, and I do things with computers, more or less effectively. I have been working with Python for about 10 years. It was a complete accident. I got into it because it was the only way I could build maps without an application crashing. And I've been building predictive models for about the last 5 years. So if you have any strong passions around Python or R, I'd love to talk to you about it after the talk. I'm also dynamic web page via the Twitters. So if you want to tweet things, that is where you can reach me. I'm also dynamic web page pretty much everywhere else on the internet. So, but with that, let's get started. So how many times has that happened to you, right? So you have one rabbit, you get another rabbit, and 1 + 1 is 2, and that's how arithmetic is done. And now that you understand this basic idea behind arithmetic, let's try it out in an actual example. And then it breaks out. This is textbook. This reminds me so much of every introductory calculus, linear algebra, and even computer science text that I was using whenever I first started learning. And the problem is that professional mathematicians and physicists, they don't work with that. Like Richard Feynman, if you're familiar with him and in his work, he developed his own personal notation system because he thought that the mathematical notation that was used in textbooks was too obfuscated, that it didn't make any sense. And there's also this lovely quote from Alan Kay, that a French mathematician got 100 of his buddy physicists and mathematicians together to ask them how they did their thing, and none of them really used mathematical notation at all. Like there's this great instance where Einstein said, I have sensations of a kinesthetic or muscular type, so he could feel it in his body whenever something was correct about an equation that he was working on. And I think that's wonderful, and that's how most of us feel about whatever our creative passions are, right? If you're creating music, you feel it in your soul. You don't necessarily sit down and you concentrate so much about the musical notes that you're writing on paper. You play and you feel and you understand it. And so there's a quote from Brett Victor in his essay Kill Math, which this is an homage to, saying, the power to understand and predict the quantities of the world should not be restricted to those with a freakish knack for manipulating abstract symbols. And I agree completely. I also think that the power to understand and build predictive models, so machine learning models and deep learning models, shouldn't be restricted to those with a freakish knack for manipulating abstract symbols either, whether it be mathematical symbols or computer symbols, right, with programming or with code. So with that, we're going to get started. And the title of this talk is called Kill Deep Math. So hopefully every apprehension that you might have had about machine learning or deep learning will be alleviated with this talk. So a roadmap, we'll be discussing some theory, then we'll be building intuition, and then we'll be looking at some code, but I promise it won't be scary code. And for the math, we'll be talking about Fourier transforms, things like gradient descent, back propagation, loss and activation functions, so maybe some of the terms that you've heard today that aren't quite as familiar as they could be. So to make math less painful, let's start with an example. Let's make this concrete with an example. Fourier transforms. Who here has heard of these? Excellent. Who is intimately familiar with Fourier transforms? Fewer hands, okay. So these transforms, Fourier series, they are expressed throughout pretty much every discipline, right? So electrocardiograms, music, so as you create sounds and as you sample things with a microphone. seismic. So my background is geophysics, and Fourier transforms were one of the very first things that we learned. But whenever I started, and even if you look at the Wikipedia articles, so this is the Wikipedia article on them, nothing about that is intuitive, right? Like this makes zero sense. And Wikipedia is supposed to be the bastion of like breaking it down, right? And that nothing about that seems to be broken down. So as I said, let's try an example. So say you have a smoothie, right? Your friend brings you a smoothie as a great snack, and you're really excited about it, but you also have a number of food allergies. So it would be awesome if you were able to have some sort of filter where you could understand precisely what ingredients went into making that smoothie, right? So you could just be given this smoothie out of the blue, and you could apply a filter and understand all of the constituent parts that were pulpified to make that smoothie. And even more, being able to extract them and rebuild the constituent fruits that went into creating it. So it's the same concept for taking an audio sample with a microphone. A microphone only samples the air pressure around it. So it gets all of the frequencies that you have added together. So A, I think it's like 440 beats per second. D would be a different sort of frequency, and it's all waves kind of oscillating at that frequency. It looks a little bit like this. So when you add all of these guys together, it gives you that yellow line up top. It takes all of the peaks, the ones above the zero axis, adds them together, and it takes all the troughs and adds them together as well. And in our smoothie example, so the yellow line would be the smoothie, and all of the constituent parts underneath it would be the fruit that comprise it. So ideally, what you would be able to do is take that signal and understand all of the constituent parts that were used to create it. And that's the entire idea behind a Fourier series. And if you look at how you would go about doing that mathematically, this is an example from a blog and a video series called 3 Blue, 1 Brown. And if you take each one of those frequencies and you wrap it around a circle, whenever you wrap it around the circle, precisely the amount of times that you would have it beating per second, something kind of magical happens. The center of mass of that particular wavelength gives a little spike in the frequency domain. And so you see here that even though the chart kind of in the middle doesn't look anything like the chart up top, you're able to determine that it's probably 3 beats per second that's making that peak. And as you see here, no matter how complex a wave might be in the time domain, if you sample it in the frequency domain, if you wrap it around that circle and notice where the center of mass pops, you're able to pick out every other little wavelength that was used to create it. And that's so powerful. It's powerful because if you have a microphone and you're outside and you're interviewing somebody on the street and you have a lot of background noise from cars that are stopping by, you would be able to understand precisely what frequency those cars are operating at and take them out of the entire equation. So you're able to get rid of the piece that doesn't make sense to you and keep the piece that you want. And mathematically, remember those creepy complex equations that I was talking about before? It really breaks down such like this, right? So to find the energy, x, at a particular frequency k, you spin, so that's the e to the I bit, your signal, the blue, around a circle at that frequency, and then you average a whole bunch of points around that path. And this makes sense to me. So all of the complex equations that we saw before, none of that made sense. But being able to break it down into plain English and color code the parts of the equation that correspond to those values, that makes a ton of sense. And then again, like if you think about d over dx, right? So if you think back to calculus, all that really is it just is a little bit of. So d over dx, x is a little tiny bit of x. or the integral is just the sum of all the little bits of. And even though the notation is kind of complex and not very intuitive, that's really all that they are. And so it hurts my heart when I see a description like this. This is from Wolfram Mathematica, and it doesn't capture any of the beauty that we just saw, right? It doesn't give you any sort of context into what could happen whenever you apply Fourier transforms to real life. All it does is just walk you through complex mathematical notation with kind of obtuse language. And I hate that. I think it's wrong, and that it doesn't really help anybody in their path to understanding. So in that vein, and remember what I just said about being able to extract constituent parts of a wavelength. I want to talk about deep learning, which usually has the same kind of struggles that you would expect to see with any sort of complex math. And let's start with artificial intelligence. And I apologize if this is a little bit of an overview of what we were discussing before. But artificial intelligence is really just any technique that enables computers to mimic human behavior. And if you go by this definition, artificial intelligence has been around for a long time. Ever since you were able to create if-else statements where you give an input to a computer and it gives you back a statement that seems like it would be correct. Machine learning is where it starts to get interesting. And that's the ability to learn without being explicitly programmed. So historically, you were responsible for giving computers rules and data, and they gave you back some sort of output. You had to have complete control over every possible situation. Machine learning is learning to learn. So you give a computer data that's been labeled, or sometimes not, but mostly data that's been labeled, and you give it the expected outputs that you would see, and then it gives you back the rules that would make that constituent part. And this is, again, very simplistic overview. You either have supervised machine learning, which is trying to predict a category, so that would be classification, or a number, which would be regression. So I'm trying to predict how many widgets I'm going to sell in July of next year. That would be a regression problem. And then unsupervised learning, that's usually clustering. So you don't know the answers, you don't have labeled data, and you're trying to understand relationships. Most of the research to date has been done in the supervised space. And that's where we've been seeing the best business value and the most recent interest in doing things with deep learning. So being able to understand what's a cat and what's a dog, that would be a supervised learning task. Deep learning is a subset of machine learning, which is being able to learn underlying features in data by using deep neural networks. So RNNs, CNNs, GANs, all of the kind of buzzwords that you've heard about, those would all be comprised in the deep learning space. And deep learning is used in a variety of ways, usually with very complex data. So you have images, and you can do object detection. You have people, and you can do face detection, so specific people, specific faces. You have the ability to bring in X-rays and automatically detect whether there are tumorous cells or in specific biology data. You can put in text. So this is an example of what it looks like whenever you take every single Harry Potter book and throw an RNN at it. It gives you back a perspective title called Harry Potter and the portrait of what looked like a large pile of ash, which, you know, given the other titles, it seems to make sense. And then you also have things like sound. So being able to take speech and automatically transcribe it with text, being able to take a melody. So just being, you know, like strumming along on your guitar and have, you know, a complete orchestral accompaniment to it created immediately. That's something called Project Magenta, which I suggest that everybody go look at if you have a lot of feelings around music, because it's very cool. And a whole heck of a lot more. So there you can see an example of taking Starry Night and juxtaposing it on the Mona Lisa. AlphaGo, so having neural networks kind of fight each other to beat a game. Autonomous driving, anything that a human can decide in less than a couple of seconds, neural networks should be able to do as well, which is so exciting, and it's really difficult to think of any sort of industry that wouldn't be touched by that. Andrew Ng, who's one of the lead instructors on Coursera, he always kind of poses that challenge to his class, and nobody's been able to come up with a good example yet. And deep learning's become so popular recently because it's more accurate than humans. So Andrej Karpathy, who is now the head of data science at Tesla, as a grad student, he went through a series of images, so hundreds of thousands of images, and hand classified each one. So this is a cat, this is a dog, this is a horse, this is a car. And he was 95% accurate. So he was the human benchmark for a long time. That's kind of one of his claims to fame for image detection. But now algorithms are more accurate than Andrej Karpathy was at image classification. We're better at language translation. We're better at being able to extract a specific voice from a room of talking people. It's really kind of crazy how much of an inflection point that we've seen and how much of an exponential uptick in progress that we've had with neural networks in the past few years. We also have specialized hardware, so FPGAs, field programmable gate arrays, tensor processing units, TPUs, which are a kind of custom silicon, so you're actually burning algorithms into the chips that you're using. And then also GPUs are getting better and better each year as well. We also have a ton of data. So I really appreciate the comment that was made in the last lightning talk about go and find data. There's a lot of it out there, and it's just waiting to be used. We also have open source tools, so things like Tensorflow, scikit-learn, Caffe, MXNet, Cognitive Toolkit. But I would argue that Tensorflow and scikit-learn have been the most impressive communities that have been built in the machine learning space. So let's try an example, because all of this just sounds a little bit like magic, but really it's just mathematics, and not the scary kind. We're all friends here. We're going to hold each other's hands. You know, none of the math that we talk about today will be scary. So very simplistic. Imagine you work at a cheese factory. And I'm using this example because every other machine learning example that I see seems to be the iris data set, which is, well, it's true and it's awful. Like it's, and I swear to God, if I see the iris data set one more time, I'm going to cry. Like it's really, it's packaged up with most every algorithm, and it's not a great use case for deep learning. And this isn't either, but I love cheese, so it makes more sense. So say you work at a cheese factory, and your boss wants to task you with predicting taste based on a number of features, so acetic acid, H2S, and lactic acid. And you have all of those variables in a CSV file, because it's always a CSV file, and you're trying to predict that last column, that taste column, without taste testing everything, though that would be an awesome job. So your super smart brains can tell how a cheese tastes, but computers are less capable. So we're going to have to use the other values, the numeric values that we have in this data set to make that assessment. So you could do something like linear regression, and that's great for doing very simplistic tasks. But the thing about deep learning is that it's great at incorporating lots of disparate data, so and also higher dimensional data, and noticing interaction effects. So for deep learning, you can have many layers of nodes, and you can also have many nodes per layer. And what those are essentially doing is acting like those filters that we talked about with Fourier transforms. It's taking every single bit of information that we have and applying different filters and tuning different knobs as you go along to try to predict whatever value that you're after. So you can start architecting something that looks a little bit like this. So you have acetic acid, H2S, and lactic acid. You might have a hidden layer with 3 nodes, and then you get an output layer like taste. So if you've heard of convolutional neural networks, they're great for images. LSTMs, long short-term memory networks, are great for spoken words. But this one that we're going to do here, just for the sake of argument, is a forward propagation multi-layer perceptron. Again, terminology, just think of it as what I'm about to show you. And each one of these neurons, each one of these circles, is just think of it as a thing that holds a number, and the numbers are called activations. So let's try it. So our first value for acetic acid was 4.543, and I removed one of the features just for simplicity's sake. So if we were going to try to predict an output using just the first two features, just the first two items in the column, we have one hidden layer with two nodes, and one output layer. And those ones that you see in each one of the lines connecting the nodes, these are densely connected neurons, is something called a weight. And we're going to assume, again, for the sake of argument, to keep things simple, that all of the weights equal 1. So all you would do is take the first node's value, so 4.543, multiply it by a weight. You would take the second node's value, 3.135, multiply it by whatever that weight happens to be, and that would give you the value for the first node in that hidden layer. You would do it again for the second node, and then you would apply the same technique to get the final output layer score. If you were doing this with something called like the MNIST data set, the values in each of the nodes would be from 0 to 1, because they would correspond with grayscale. But again, just assume, since we're trying to keep this simple, we're trying to learn based on the input features that we have. And machine learning really is just finding the right weights for each of these little lines going between the nodes, and finding the right biases, so what kind of functions you would apply to the nodes. And we'll touch on that a little bit later. So if you wanted to code this, it would look something like this. You would build a NumPy array, you would have the associated weights for each of the nodes, you would sum them together, you would do the same for the hidden layer, and then you would receive some sort of output, and that would be the estimated output that you have. But there's a problem with this. And if you look at the problem, it's great that we had these two features and we were trying to predict the output, but our actual value for that score was 12.3, not 15.356. So we can do better. And a way that we can do better is with something called an activation function. And an activation function can look like a variety of things. They can be linear functions, they can be nonlinear functions, but the one that's mostly used in industry today is something called a ReLU. And this is a rectified linear of activation, but mostly all it does is if you have a negative value, it gives you a 0. And if you have a positive value, it just gives you that value itself. So if you have a ReLU of this value right here, this 4.543 plus 3.135, that would be the 7 value that we had in the first node of our hidden layer before. You can use as many of the activation functions as you would like, but the ReLU is the industry standard. So the takeaway is that deep learning is just math. It's a lot of handcrafting for specific values, but ideally none of that is done by you. It's all done by whatever algorithm you select, by whichever machine learning or deep learning algorithm. And the neural network automatically creates weights, tries out a whole bunch of different ones, and tries to interpret them to make predictions. So if we go back to that example, right, so you could take the predicted value minus the actual value, and you get back something like a 3.056. And in higher dimensions, this is very low, right? So just two dimensions that we're trying to predict on. But in higher dimensions, predicting gets hard. And at every set of weights, there are many values of error and bias and weight for each particular node. So this is a little bit more complex of an example, right? So it's taking in all three features, all three columns in the data set. It's adding 3 hidden layers with 7 nodes per layer. And just for this simple example, you end up with about 150 variables, 150 parameters that you have to tune and twist and handcraft and tweak to get that one answer, that taste prediction. And that sounds terrifying as heck to me. Right? Like if my boss came to me one day and said, hey, Paige, I want you to try out 150 different potential variables and parameters and different combinations and give me the best one. Like that sounds like it would be a really hectic and awful weekend. But for predicting that number, for a simplistic example, just imagine how much more difficult that it would be to predict pixels and to predict specific images. So the way that you would architect that solution, so if you don't have a specific numeric value that you're using, is that you would take each pixel in that image. So say you have an image that's 1024 by 780 pixels. Each one of those pixels would be an input node. So in this one, we have 3 input nodes, right? For a 1024 by 780 picture, you would have 800,000 almost input nodes. And that's kind of insane. And that also points to why you would need specialized hardware and lots of compute capacity to do these calculations. It's very, it sounds like it would be complex, and it is, because it's a lot of numbers, but it's a lot of numbers all doing very simple things. They're just being multiplied together and added together. Just multiplied together and added together, and it's just math. So for every single one of those nodes, again, the equation looks kind of scary, but really it's just weight times value in a node plus weight times value in a node plus weight times value in a node, and then that sigma that you see there, that yellow, is just whatever activation function you apply. So if we use the ReLU example, if everything kind of is negative, then it would be 0. If it's positive, then it's just that value itself. And this works the same way for numbers, same way for images, same way for sound. And in matrix notation, because a lot of people like using matrix notations instead of having to write out every single one in one single line, it looks like this. And again, it's just take a number for a weight, multiply by the node, add it all together. If you look at it in a paper or in a textbook, it looks like that. And nothing about that is intuitive. Absolutely not. And again, it hurts my heart that this is what is expected for students to learn as they're trying to understand deep learning. Again, that's just kind of a simplified example, right? So number, multiply by weight, and then apply the ReLU. If you'd like to play with this yourself, I highly recommend going and looking at the Tensorflow Playground. It gives you the ability to add nodes, add layers, and change activation functions. So instead of using ReLU, you can use tanh or a sigmoid, and try to see how you would predict how that influences the predicted output that you would have for a model. It's really interesting as a learning tool, and it's all in the browser, so you don't have to download anything at all. There are also some other things that we're not going to get into with mathematics so much, but something called a loss function. And the loss function is basically whatever, so mean squared error would be an example, and it's how far off your predicted value is from the actual value. And a way that you can help minimize loss is through a concept called gradient descent. And an example for this would be, say you're on a hill. So you're on a hill, it's pitch black, dark, you can't see anything. And you know that your house is at the bottom of the hill in this valley. So what you could do if you couldn't see is you could feel around you, and you could assume that whatever slope is the steepest is probably the area that you should move towards if you're trying to get to the bottom of the valley. You move, tiny little step, you feel around you again. Where's the slope the steepest? You move that direction, and eventually you hope that you'll get down to the end of the valley. And that's true, fingers crossed, hopefully. It also might be that you end up in a different minima, a different local minima, if you remember that from pre-cal. But for the most part, you're just trying to find one of the minimum values in this three-dimensional space. And to calculate the gradient descent using slope, you would just do 2 times the predicted minus actual value, and then multiply it by the learning rate. And again, all of this is very simplistic math, right? It's just take a number, multiply it, minus it from something, and then you get the value that you're supposed to be. It's just y equals mx plus b type stuff, right? So things that you understand from grade school. Backpropagation gets a little bit more complicated. So trying to estimate the slope of the loss function with respect to each weight gets a little bit more into calculus. But for feed-forward networks, really you just need to conceptually understand the calculating the loss function. And again, with backpropagation, you start at some random set of weights. You've used forward propagation, so that concept that we were showing before, to make a prediction. You use backward propagation to calculate the slope of the loss function. And what this is doing is it's looking at all of the assessments that you made for each node, and it's preferentially paying more attention to the nodes that were telling you the truth. So you could think of it as kind of like BS detection, right? Like you're looking at the nodes that are telling you the truth, and you're paying preferentially more attention to them, and the ones that were telling you falsehoods, you're just saying like, okay, not paying attention to that guy, obviously not making good life choices. So that's all backpropagation is doing. So this concept should all look very familiar. And this is from a guy named Chris Olah. He got one of Peter Thiel's scholarships to not go to school, to just kind of go forth and be awesome. And he's been working with Google Research for the past several years. But a neural network with a hidden layer has a universality, which is that given enough hidden units, it can approximate any function. And this is very, very similar as a motivation to the Fourier series, and that no matter how squiggly and complex your line looks like, it really is just a sum of a lot of very, very simple frequencies. And all you have to do is just kind of extract out those values, and you're able to describe anything, no matter how complex it happens to be. So if you have any interest in this, I know I'm creeping close to time, but you can look at something called Tensorflow with Keras. And Tensorflow is an open source machine learning framework that was created by Google. It's good for a number of things, so not just deep learning. It's good for basically any numerical computation task from partial differential equations on up. But it's very kind of strange and scary to look at TensorFlow code because it's obfuscated, lots of boilerplate, hundreds of lines to do a thing. So Keras makes that easy. Another takeaway from this talk should be that you should never use TensorFlow without Keras, because 200 lines of TensorFlow equal about 10 lines of Keras. And the language is very straightforward to use. It was by a guy named Francois Chalet, who now works at Google. And like I said, user-friendly API, lots and lots of notebooks available for you to use. I also have one listed up on my site if you want to get started. And it's designed for human beings, not machines, focused on user experience and making things less obfuscated. So some sources and inspirations for today's talk. Chris Olah's blog, Brett Victor's Kill Math essay, 3 Blue, 1 Brown, which goes through and explains many complex mathematical topics in straightforward and visual ways. A Student's Guide to Maxwell Equations, which is one of my favorite textbooks, and also the Tensorflow Playground. So I highly recommend that if you have any interest in kind of de-obfuscating mathematics, and you can see the beauty in it, these resources have been very, very close to my heart. And if you have any questions about deep learning or machine learning, I'm always ready and willing and happy to answer them on Twitter or through email or whatever. So thank you so much, and hopefully this was useful.